So I'm going to expect to go on for including discussion until about 3:30. I know that some people need to leave. You should feel free to go. Okay, let me talk about gravitational wave observations. This is the subject in which most of my energy went into this subject, plus the theory of time machines, during the period from about 1970 on up until about 2000. So there are three different frequency bands in which we expect to see gravitational waves in roughly the next 10 years. One is the band from 10 hertz to 10,000 hertz, which I like to call the low frequency or the high frequency band. This is a band in which we see black holes with masses that are so-called stellar mass black holes, 2 to 1,000 solar masses. And we expect to study these kinds of black holes using ground-based interferometers, which I'll talk about in a moment. Space-based interferometers will study black holes between 10,000 and 10 million solar masses, with wave frequencies or wave periods, say, from 10 seconds up to a few hours. Then the technique of pulsar timing, which I'll talk about at the very end. We expect to study black holes between 100 million and 10 billion solar masses. These are the largest black holes that we believe exist in the universe, with wave periods between about a month and 30 years. So a laser interferometer gravitational wave detector operating in the high frequency band consists of 4 mirrors that hang by wires from an overhead support along the arms of an L, orthogonal arms. Gravitational wave tendexes push these mirrors apart and pull these together. Here is the gravitational wave coming in. The stretching tendexes are along this arm, the squeezing tendexes along that arm. As the wave oscillates, the red changes to blue, the blue changes to red. These mirrors that are being pushed apart get pushed together. These that are being pushed together get pushed apart. These oscillations for these instruments, we are sensitive to frequencies between 10 hertz and 10,000 hertz. That's high compared to the 1 hertz frequency of swinging of a pendulum. And so these mirrors behave as though they're free masses. The restoring force does not have much influence. The laser beam is sent in through a beam splitter. It goes through this mirror. There's an anti-reflection coating on this face of the mirror, a highly reflecting coating there, highly reflecting here. So this forms a Fabry-Perot cavity between these mirrors. Fabry-Perot cavity 4 kilometers long. This cavity is maintained at a half-integral number of wavelengths separation, so the light basically gets sucked into the Fabry-Perot cavity. It is stored here for a time of about 1/100th of a second. And then it leaks back out from the 2 arms. Because this arm has increased in length, that has decreased in length, there is a phase shift put onto this light. And that phase shift, different phase shift on the 2 arms, causes a change in the intensity of the light going to the photodetector. Standard interferometry, optical interferometry. As the waves oscillate, then the intensity into the photodetector goes up and down as the waves oscillate. So the team I work with has been computing the gravitational waveforms. The separation in these mirrors, delta L is H times L, or h is basically the second time integral of the tidal field. And so we're looking at second time integral of the tidal field as a function of time. There are two different waveforms, just as there are two polarizations for light. This is the particular waveforms that you get when you have a 60 solar mass black hole spinning at 91% of the maximum possible. A 10 solar mass black hole spinning at 30% of the maximum possible. Here are the spin axes, the circular orbit. This is an example of a black hole binary. These are the waveforms that you get out. And we are building a catalog of waveforms for various black hole masses and spins. There actually are 7 free parameters here. 3 parameters for each spin, and then a mass ratio. So 7 non-trivial parameters. And for each choice of those 7 parameters, you get a set of 2 waveforms. We are in the process of carrying out 1,000 simulations to build a dictionary that tells you when you see a particular waveform, what was the black hole binary doing? What were the masses? What were the spins? How were the tendexes behaving? How were the vortexes behaving? The goal then is to use the waveforms that we get from the simulations in the data analysis for these instruments. This, to give you some numbers, when these waves reach the Earth for the black hole binaries, we expect the second time integral of the tidal field, this h, to be less than or of order 10 to the minus 21. We multiply that by the separation between the arms, about 4 kilometers. The product is the changing separation of the mirrors. And that product is 4 times 10 to the minus 16 centimeters. So these instruments have been operated with noise levels of 1 times 10 to the minus 16 centimeters. That's 10 to the minus 3 Fermi, 1/1000th the diameter of the nucleus of an atom. And that's the accuracy with which this team monitors the changing separation of these mirrors. What they're really sensitive to is the motion of the center of mass, the relative motion of the center of masses of the mirrors, because you're averaging over the face of a mirror with a laser beam that has about this size. So you average over a huge number of atoms. You're averaging for times of about 1,000th of a second, which is a very large time compared to the, say, 10 to the 13 hertz Debye frequency for the oscillations of the atoms in their lattice. And so you're averaging away everything except the center of mass motion of the mirrors. So you're monitoring the center of mass motion of these mirrors relative to each other to a precision of 10 to the minus 3 Fermi. There is now a network of ground-based gravity wave interferometers that are doing this, going after black holes between 2 and 1,000 solar masses. We have the project that was founded by Ray Weiss at MIT, Ronald Drever, and me at Caltech in the early 1980s. We have instruments in Hanford, Washington, Livingston, Louisiana, and then associated with us also the GEO 600 instrument in Hanover, Germany. There's a French, Italian, Dutch collaboration, has a 3-kilometer interferometer in Pisa, Italy. In Japan, they are beginning to construct, well, it's no longer called LCGT, but they're beginning to construct a 3-kilometer interferometer in the Kamioka mine in Japan. And we just received approval last week from the National Science Board in the US to move one of our 3 LIGO interferometers to India, probably near Bangalore. We have 2 interferometers at present in Hanford, Washington, 1 in Livingston. We will take 1 out of Hanford and move it to Bangalore. So this gives us then a worldwide network. We need this network for confidence that anything we see is a true gravitational wave. You should see the same kind of signal in many different instruments around the world. We get the direction to the source by the time delay in arrival of the signal at different sites. And by having a worldwide network, we get good angular resolution over the sky. Well, not very good. Angular resolution of about 1 degree typically. Sometimes a little better, sometimes a little worse. And we need this network for extracting both waveforms from a given gravitational wave source. These are pictures of the LIGO interferometers in Hanford, Washington, Livingston, Louisiana, 4-kilometer long arms inside these vacuum pipes. And our GEO 600 instrument in Hanover, Germany, is used for advanced technology development. At any given stage, we run in this system interferometers that are using the technology of the next generation in preparation for moving that next generation technology into the big interferometers. LIGO, although it began as a Caltech-MIT collaboration, it's now a collaboration of 850 scientists, 75 institutions in 13 nations, directed by David Wrightsey, who's at Caltech. Gabriela Gonzalez at the University of Florida is the spokesperson. When we originally proposed building LIGO, our proposal in 1989 said we would do this in 2 steps. We would build initial interferometers with a sensitivity where it is plausible but not likely to see waves. So if we were lucky, we would see waves. And then we would upgrade to advanced interferometers, which would have much better sensitivity, where it is likely to see waves from many sources. We had to do this in 2 steps because these advanced interferometers were so sophisticated and so complex. We did not think we could build them successfully without first building a simpler set of interferometers and operating them first. So that was the reason for doing this in 2 steps. Our initial interferometers were built and operated for 5 years between 2005 and 2010. We were able to see black hole merges out to 300 million light years, far enough that there are roughly 100,000 galaxies within that distance. We have not seen any gravitational waves yet. We're still analyzing the data. We have interesting limits on them. The advanced interferometers, we began installation in October 2010, 2 years ago. Installation is nearing completion. The light is just beginning to send light down the arms, one of the arms of the interferometers. This process is a long process because these are very complicated instruments. Just imagine operating at 10 to the minus 3 Fahrenheit. It's very, very difficult. And so we expect to be at or near design sensitivity by 2017, based on our past experience. We will then see black hole merges out to 4 billion light years, where the expected event rate is between 3 a year, roughly, and 1 a day, or very roughly, and many other sources. In 1989, when we proposed to build LIGO, we said this is the noise curve that we will achieve. Here I'm showing the square root of the spectral density of this H quantity, the second time integral of the tidal field. So it's a dimensionless strain in space per root hertz as a function of frequency. What these numbers mean is that if you go to the minimum here, where that's about 2, 3 times 10 to the minus 23, that's per root hertz. You multiply by the square root of the frequency, which is about 200 hertz. And you get up to something like 5 times 10 to the minus 22. That's the RMS noise in a bandwidth equal to frequency, 5 times 10 to the minus 22. And gravitational waves, the strongest waves we expect to see, are of order 10 to the minus 21. So we are in the region where we need to be, but just barely in the region where we need to be. But it's impressive that the team has succeeded by 2007 in achieving this design goal, except in a small corner down here where there were technical problems. Carried out a gravity wave search from 2005 to 2007 with no detections. We expected to begin installing our advanced interferometers at that time in 2007. However, in the first George W. Bush administration, among many other things that happened under Bush, there was a 3-year delay in the new starts for new projects all across, in science across the government. So we lost 3 years, and in those 3 years, we just took those extra 3 years and improved these first interferometers by about a factor 2, carried out a second search, and we are currently analyzing those data. And then we began installation in October 2010, and this is the noise curve. This is our design noise curve. About 10 times better, really about 15 times better noise than in the initial interferometers. When you go from the initial interferometers to the advanced interferometers, let me tell you something about what happens in the technology. The initial interferometers have 11 kilogram mirrors made of fused silica quartz that hang by a steel wire from an overhead support. The advanced interferometers have 40 kilogram mirrors that hang by a fused silica fiber from a mast that hangs from a mast that hangs from a mast that hangs from an overhead support. So it is 4 cascaded, 4 successive pendula, which provides you much better isolation for motion of the ground. In the initial interferometers, we had 10 kilowatts of optical power in these Fabry-Perot cavities. The advanced interferometer is about 1 megawatt. Imagine the technical problems of dealing with 1 megawatt of power bouncing off a mirror. Huge technical problems. But do we think that they are all solved? In the initial interferometers, we had the kind of optical configuration I showed you with 4 mirrors, but one more mirror here that basically takes light that is leaving the interferometer, going back toward the laser, and recycles it back into the interferometer. In the advanced interferometers, we recycle some of the signal light back into the interferometer using another mirror. And this, by adjusting the reflectivity and position of this mirror, we can change the shape of the noise curve. We can go from, for example, from a noise curve with this shape, this function of frequency, and this is the noise level, to a noise curve with that shape if we want to look for gravitational waves from, say, a pulsar at 600 hertz. Then we just change this one mirror. This is a much more versatile configuration. The advanced interferometers have active vibration isolation, whereas the initial interferometer is just passive vibration isolation. So this is much more complicated, and you can understand why we did not want to do this at the beginning. We had to have the simpler configuration in order to be successful. As an example of the experimental challenge for the advanced interferometers, here we must monitor the motions of 40 kilogram mirrors to a precision that is approximately the half-width of the Schrodinger wave function of the center of mass degree of freedom of the mirrors. This means that in LIGO, advanced LIGO, we will be watching these mirrors move with them behaving like quantum mechanical particles, although they each weigh 40 kilograms. And in the design of these instruments, we have had to take that into account. We have to use quantum measurement theory in the design of these because we are dealing with 40 kilogram quantum mechanical particles. So for the first time, humans will see human-sized objects behave quantum mechanically, just because we're making such accurate measurements. This requires a new form of technology called quantum non-demolition technology to enable us to get a classical gravitational wave signal through 40 kilogram quantum mechanical particles and out in the output of the photodetectors without the quantum properties of the particles, of the mirrors, destroying the signal, demolishing the signal. This is a branch of modern quantum information technology. Quantum non-demolition is a piece of quantum information technology. I'm not going to go into the details. I just want to tell you there are many other sources besides black holes that we will study with our advanced LIGO detectors. And we will do it in a multi-messenger way in collaboration with electromagnetic and neutrino astronomers. We'll watch black holes tear neutron stars apart, see the gravitational waves, the gamma rays, the neutrinos, an optical afterglow. We'll see the disturbed accretion disks in the case of black hole binaries. We'll watch neutron stars spiral together, collide, and merge, and collapse to form a black hole. Again, we'll get gamma rays, neutrinos, and optical and radio afterglows. We'll watch supernova being triggered by the collapse of a normal star to form a neutron star. Again, optical, radio, gamma rays, neutrinos, as well as gravitational waves. Spinning neutron stars and cosmic strings, that is, fundamental strings that are expanded in the inflationary birth of the universe to cosmic scales. And that when they pass through each other, reconnect, forming kinks that travel down the string at the speed of light, emitting gravitational waves. These are examples of the things that we are going after with our advanced detectors. The optical astronomers and radio and X-ray astronomers, gamma ray astronomers are all preparing for this multi-messenger era. At Palomar Mountain, Caltech also owns and operates the Palomar Observatory. Sri Kulkarni has built the Palomar Transient Factory, which is trying to characterize the transient optical bursts of radiation, suddenly changing sources in the sky, some of which will be gravity wave sources, most of which will not be, but try to understand these in preparation for a few years from now when we're doing joint observations between the optical telescopes and the gravity wave telescopes. There's a 48-inch Discovery telescope that in an automated way scans the sky looking for something to change. When it sees something change, it sends a signal to the 68-inch telescope, which in an automated way turns and looks in much greater detail at that source. The results then are sent to astronomers who are observing on the 200-inch telescope and on other large telescopes around the world. There is follow-up, spectroscopy follow-up on one or another of 14 different follow-up optical telescopes, big telescopes around the world. So this is what is happening now. This is being used to characterize the optical transients in preparation for multi-messenger astronomy. I'll just wind up by saying then that there is also this, in the planning stages, the observations of gravitational waves in the low frequency band, black holes 10,000 to 10 million suns, by 3 spacecraft that track each other with laser beams, 1 million kilometer long arms. This is the European Laser Interferometer Space Antenna, or ELISA. The technology for this will be tested in what is called a Pathfinder spacecraft flight in 2014, and ELISA will fly 2022 or later, probably later. These things take a long time. Among other things, ELISA will see small black holes orbiting around large black holes, spiraling in, and as they spiral in, they emit gravitational waves that carry a detailed map of the space-time geometry, of all features of the space-time geometry of the large hole that is being sampled, it's being studied by the small hole as the small hole goes around. These holes might have a size something like this, 5 million kilometers, 10 solar mass black hole going into a 1 million solar mass black hole, 3 billion light years from Earth. LISA itself, approximately the same size in our solar system, 1 million kilometer separation. Separation is monitored with laser beams to a precision of 10 to the minus 9 centimeters. In the final year, this small black hole will make 100,000 orbits going from here to there. And those 100,000 orbits will carry very, very detailed information about the big black hole and about what's going on with the orbit. I'm going to skip over this. And finally, pulsar timing arrays going after gravitational waves in the very low frequency band, 10 to the minus 7 hertz to 10 to the minus 5 hertz, roughly a graduate student lifetime for a graduate student thesis. Looking for supermassive black holes, 10 million, 10 billion solar masses. The way this works is the radio astronomers are studying simultaneously radio waves coming from many different pulsars on the sky, an array of pulsars. Gravitational waves go over the Earth, and they produce an analog of a changing index of refraction as they go over the Earth. But a changing index of refraction is different for the radio waves that come in from this direction versus that direction versus this direction. And so as a result, you see in the timing of these very regularly separated pulses, you see a speed up and a slow down, speed up and slow down in the pulsars, all synchronous, the same pattern, but with an amplitude that is different depending on the direction of the source. And you know it's a gravitational wave if the pattern, if the amplitude has just the right behavior on the angular direction to the source compared to the direction of the gravitational wave. This is being pursued by a worldwide collaboration of radio astronomers throughout the world, primarily Europe, Australia, and North America. And they already have a sensitivity good enough that they are competing with LIGO to be the first to see gravitational waves. It is not clear who will win. They both will almost certainly succeed within the next few years. So let me just conclude, and then we can have just a few minutes of further questions. Highly dynamical black holes show an amazing richness of structure and behaviors, of geometrodynamics. Their vortexes, their tendexes. Numerical relativity is now a powerful tool for probing this geometrodynamics. Gravitational waves and multi-messenger astronomy will bring this rich physics and much more into the realm of observations. So this is really an exciting period of time for me. From a personal point of view, this is the culmination of much of my research career, this combination of what is happening with these numerical simulations and what is happening with the gravitational wave technology and observations. Thank you.
Thank you very much. That's terrific. I just thought that I can behave like quantum mechanical one day. Any question? Yes, please.
จะแปลหรือว่า
ภาษาอังกฤษ
when the black hole are colliding, how about the singularity of the black hole? When the singularity merges, is it simple or complicated event?
So the question then is, what happens with the singularities inside the black holes when the black holes collide and merge? The answer is we don't know. The simulations that have been done have all been focusing on the exterior region, the horizon, they go just a small distance below the horizon. The tools of numerical relativity are now sufficiently mature that this kind of question can be asked. How would the singularities behave as the black holes collide? But nobody has yet applied the tools for this question. This is one of many other questions, of very many interesting questions about geometric dynamics that will be studied in the next few years.
Any other questions?
Maybe non-physics question. For a student, I mean undergrad student that interested in gravitational wave and black hole physics, what is your suggestion for where is a good start for them?
Suggestion for
Where is a good start for them? I mean,
Good
which
start?
field in physics, which subject do they have to learn, or what kind of tool? They have to
okay, so if you're interested in black holes or gravitational waves as an undergraduate, what subjects do you need to study?
Yes.
So I think if you think about the things that I have described, quantum physics is very important for the gravity wave detectors. Quantum measurement, which is only treated very briefly in textbooks, but it is crucial. Elasticity theory is very important for these detectors. Signal processing, statistical mechanics, the so-called fluctuation dissipation theorem is used over and over again from statistical mechanics in the design of these detectors. The optical signal, optics, modern optics, and nonlinear optics particularly. So a large range of different physics goes into these detectors. The black holes themselves, if you're not interested in the multi-messenger part, only the black holes, then it's simpler. You need to understand general relativity very, very well. But let me describe what the problem was in these simulations. You also need to have some understanding of numerical methods. People started trying to simulate black hole collisions in around middle 1960s, or early to middle 1960s, and had great difficulties for several decades. And in the end, it turned out that the biggest difficulties were because the people doing this did not understand the mathematics sufficiently well. The relationship between the so-called constraint equations and the dynamical equations. It turned out that when you used the methods that everybody was using, and you solved numerically these constraint equations, then you evolved forward in time with the dynamical equations. Errors, tiny errors, small errors in solving the constraints grew exponentially. And the calculation came to a crashing halt, the computer crashed. And the mathematics of why this happened, the fact that it happened, and how to fix it, this is very deep issues in applied mathematics. And so for success, the people doing, the physicists doing the simulations, they had to go to very good applied mathematicians to understand this. So black holes themselves, you need general relativity, you need differential geometry, differential topology, and numerical methods if you want to understand the modern work in black holes. But some of the most exciting work will be done with the multi-messenger aspect of this, where you have the neutrinos, the gamma rays, X-rays, optical, radio. And this involves all of the tools of astrophysics combined with general relativity. So I think it is true that astrophysics, once you go beyond just the black holes, and gravitational wave technology, altogether they involve essentially everything there is in physics in one way or another. But the place where you can most easily the thing that needs the least physics is probably the black holes classically. General relativity has a reputation of being very difficult. It's not nearly as difficult as plasma physics or quantum gravity. But if you want to go beyond just the classical black holes, you have to have all of this, the rest of this physics. So, in brief, the answer is you need to get a very good understanding of the foundations of all of physics.
Just good at everything. Any other question? Please.
Yeah, so recently there has been a discovery called BEC, and I think that's been an
I'm sorry, discovery of
Bose-Einstein condensation. And I think they also try to apply it, maybe sort of like application on trying to find a gravitational wave. So I don't know if have you looked at it and can you comment on that?
So from boson stars?
Bose-Einstein condensation.
Oh, for Bose-Einstein condensation.
And I think I went to the talk and they were trying to sort of like make it interferometer. And then I don't know if that's possible and can you comment on that?
Okay, so Bose-Einstein condensates enable you to build a basically classical field in which the quantum carriers of the classical field are bosonic atoms. And so you can then build an atom interferometer in which the analog of a classical light wave is a Schrodinger wave function for a boson condensate of bosonic atoms. There is a very interesting program in this direction for gravitational wave detection being pursued at Stanford University. And this is very promising in the more distant future.
So is it possible?
I think it's possible. It appears at the moment that the frequency region, gravity wave frequency region, where this may be the best, is sort of between LISA and LIGO. It is a frequency say around 1 hertz. But gravity wave detection is extremely difficult by this technique, just as it is with light. And the time until you have real working gravitational wave detectors by this technique is some years in the future. It's probably a decade at least in the future. It would be my personal guess. But this is a very promising approach. And atom interferometry is a very exciting field for high precision measurement. It has many, many other applications, as you probably know.
So is worth pursuing in these areas of interest in the future? I mean, is it worth?
Well, I think it's very much worth pursuing this, but I think if one wants to pursue this field, you want to look at all the other applications, for example, to very stable frequency standards, getting very, very stable clocks, and there are many other applications. I think that Bose-Einstein condensates and atom interferometers are just a major, very exciting direction for your generation of physicists.
Thank you.
Another good idea for writing proposal. Any other question, please? Okay, maybe we will give you to rest and maybe ask some other question behind the scene. Actually, we have some gifts that we'd like to, for the thank you gift, that we'd like to ask the chairman of the department, Dr. Physics, to give you the gift. This is a picture that actually taken by one of our staff, standing right here. He will let me tell you, but I'm going to tell you.
Beautiful.
All three are taken from different years. It's very difficult to get the right shot and have the early sample right in front of the movies.
Thank you very, very much. Can you so you tell me, so when did you take these?
Different time of the year, different years. I understand here, the university here. ศาสตร์
down behind the mountain. To the top of the mountain.
ขึ้นน้ำตก
For some